Good morning to everyone. I'll be taking lectures on design of biophotonics devices. I'm Nilesh Vasa from Department of Engineering Design at IIT Madras. Now, the reference books which we will be focusing on based on the topic of design of biophotonics devices. One book which is written by Professor Parasin Prasad, Introduction to Biophotonics, and another book is Gerard Kaiser, which is who has written book on biophotonics concepts to applications. So mainly we'll try to focus on the topics concerning biophotonics and the subjects, the overall course content in general is basically we'll start with light tissue interactions, tissue optical properties, light sources, detectors, free space and optical fiber based sensors, spectroscopy based devices mainly towards visible infrared spectroscopy, etc. And then we will also discuss in detail optical coherence tomography technique, which is very useful for various imaging modalities related to optical approaches, so and photoacoustic tomography techniques. Subsequently, we will also talk about light tissue interactions. So these are the main four we can say sections under which we will try to cover various aspects related to biophotonics. Now, starting from introduction aspects related to this introduction to biophotonics. So if we try to we cover this aspects, basically we know that, so we will talk about interaction between light and biological tissues. So light, that is basically photons, or electromagnetic wave, photons, when they interact with biological tissue. Now if we talk about this subject, basically biological materials or tissues, or materials we can say, so it is basically either we can say it's nothing but biophotonics, and in some books they also described as under biomedical optics. Okay, optics. Now we know this photonics is the discipline which deals with, as such, basically we can say generation, generation and detection of photons. In some cases it's also controlling, control of photons, for a certain functions, for a certain functional requirements, for a certain function. Okay, we will discuss how exactly this aspects comes into picture, and what basically photons, how are they going to help us? One, in terms of transferring and processing information. So and processing information, very much similar to the communication aspects. The second aspect point is sensing and measurement, and and the third one is basically modifying, right, physically modifying the material itself, right, modifying material characteristics. So, how exactly, right, this aspects comes into picture? This basically in this class we will try to learn through photon and right material interactions. So, when we talk about this aspect, photon and material interaction. So, how exactly, right, for photon interact? So, let's consider, right, a tissue, right? Tissue or an organ which is right is made up of cells, right? The organ. Now, when electromagnetic wave, or in our case photons, incident light, when photons interacts with this tissue, what are the phenomena related to optical, right, system that we will observe? One is reflection. We will see a reflection, right, which, right, reflection we'll see this, right, when light interacts with this tissue, some reflection will come into picture. Now, some part of the light will also, right, get transmitted through this, right, medium. When the light is getting transmitted, there, right, it may interact within this tissue material, and what we will see is either we will also observe scattering of light. Okay, so we will observe scattering of light. Okay, and we'll see what are the different types of scattering, right, that we can observe, and we will also observe that there will be, we will also notice, right, some absorption coming into picture, right. So the intensity of the light will get reduced, right, in turn. So there will be absorption which is due to the material characteristics, right, tissue material characteristics. Okay, and hence what we will see that the transmitted light intensity, right, input is, let's say, intensity of the light with wavelength lambda and a frequency nu. The transmitted light intensity will be smaller than the input, of course, because of the absorption coming into picture over and above, right. And what else that we will observe is refraction, right. In some cases we will also observe which also may be associated with scattering as well. So some refraction also we will observe, refraction. Okay. Okay, so and this is, as I told you, overall transmission, right. So, okay, so biophotonics as overall, right, it basically deals with interaction of photons with the tissue, and then observing either reflection or scattering, or measuring some scattering or transmission or absorption characteristics over and above. It may also deal with the absorbed light, right, or photons in this material may also get involved in modifying the material characteristics as well. So these aspects, right, overall these aspects, whatever we are seeing here, are very useful for sensing, right, measurements, right? And as I told you, right, material modification, okay, to certain extent, of course, but it is possible. Now coming to the next, right, based on this, what we can right think about different applications, right, applications of this right, biophotonics applications, right, which is one, it is imaging modalities, right? We can make use of those photons to image the tissue structures or biological, right, organs, etc. Imaging modalities may be in the form of 2-dimension or 3D, 3 dimensions, which for tissues, organs, etc., right, organs, etc. It is also related to sensing and measurements of some of the physical parameters associated with this, right, interactions, okay. It can be parameters, some physical parameters, right, or some of the, right, metabolic activities, etc., in form of, let's say blood oxygen, right, or even glucose measurements, right, or we can also capture the, as I told you, some of the physical parameters related to indirectly, of course, related to blood flow, okay, etc. Okay, so these are all outcomes related to, right, application outcomes related to sensing and measurement. It's also possible for a therapeutic, right, approach, therapeutic, right, photo treatments, okay. So that means we make use of this photons towards, let's say, healing of injured cells, or treatment, right, or ablation, etc., of the some of the tissues, etc. That should be possible, okay. And what else that we can do based on this imaging, sensing, therapeutic treatments? What we are going to achieve is, right, some of the, as I told you, we can use this approaches towards diagnostic purpose, right, or monitoring purpose, right, or basically therapeutic, right, purpose, right, applications. So imaging, sensing, measurements, therapeutic treatments are useful in terms of diagnostics, monitoring, therapeutic purpose. Now monitoring can be of different types, okay, in vivo, right, ex vivo, in vitro, etc. However, it should be possible based on this interactions, okay. Now this area related to what we are talking about involves, this biophotonics area also involves, okay, it involves various fields associated with, right, we can say science and technology in terms of biology, right, biology, in terms of biology, chemistry, of course physics, because right, photons, right, aspects, etc. And then in biomedical aspects, medicine, right, and biotechnology with cellular, right, aspects, and then we also did with engineering concerning devices, engineering and technology. Okay, so this aspects that are indirectly, right, covered. Photons will interact with, right, cells, tissues, some organs, etc. So wherein biology, biotechnology, etc. comes into picture, depending upon the photon energy. This aspects related to either chemistry or, right, chemical reactions, other chemical activities, etc. can be controlled. It is also possible to control, right, use it for measurement, sensing towards medicine and biomedical applications, etc. And as the light interactions are, right, are governed by physical laws, so physics is coming into picture. The devices associated with biophotonics are taken care through engineering and technology. So it's the combination of all these fields, areas, which helps us to, right, use biophotonics for various, right, biomedical applications. Now the advantages we can say of this approach, biophotonics approach, is first of all, photons and light matter interaction is possible non-invasively, right. It's a contactless, it will provide contactless measurement, right, and to the certain extent it is non-invasive, right, non-invasive. We can transmit the light or photons in free space or via optical fibers or waveguides, optical fibers or waveguides, right, to certain, right, gain position and capture the information, right. It also allows photons with wide different frequencies, right, photons range with different frequencies and wavelengths, wavelengths for, right, different applications. Okay, so this are the features we can say of biophotonics, and that's they are so attractive and useful towards, right, use for measurement, sensing, diagnostics purpose, and hence we have interest, right, in using this devices, biophotonics based devices, for biomedical applications. It may be so overall, right, these devices are useful for measurements at molecular level. We will see some examples in our, right, subsequent lectures. So measurements at molecular level, or, right, bacterial or virus, right, level measurements through fluorescence or through other means. Okay, we can at cellular level, right, or tissue level, right, we can measurements, right. So and at organ level, right. So it's molecular level, nano, right, meter levels to micrometer, micrometer level, right, nanometer level to micrometer level to millimeter level, right, order it should be possible, right, biophotonics this devices. So these are very useful, right? Wide range measurements are possible with, and that too contactless, right, non-invasive approaches. And because of this, how this tools, biophotonics tools and techniques are being used in terms of biomedical applications. So it is ranging from, we can see, right, we can we can go into specific applications, but let's say clinical applications, right. We can also use, now clinical applications can be, it may be measurement related to dentistry, dermatology, right, dealing with skin tissues, dentistry dealing with the teeth, right, and gum tissues, etc. It is also possible for point of care analysis. So one very typical example is pulse oximetry, right, which it is useful for environmental monitoring, right. It is useful for pharmaceutical applications, that is drug development, right. Photonics techniques are used extensively for analysis, right, and drug development applications as well, and of course control of, right, some of the biomedical processes. So we may use measurement techniques based on optical approaches for controlling the process parameters, etc. And these applications related to biomedical applications are not only limited to dentistry or dermatology. We can extend in terms of biomedical applications further down to let's say to cardiac, right, measurements, cardiology, right, cardiology. So it is for imaging. Let's say what a typical application that we can think about is imaging of right, atherosclerotic we can say a sclerotic plaque, right, plaque, or right, tissues, such tissues, diagnosis of heart functions, okay. Monitoring and right, surgery related, right, monitoring, etc. We can right, through imaging modalities, etc. And recently reducing even cardiac right, applications towards photomodulation techniques for reducing cardiac, right, pain. It is possible. Now coming to the next level of application, dentistry. When we talk about dentistry, we can, right, apply for detection of caries, right, cracks in teeth, cracks in teeth. We can even detect micro, right, level caries, etc. Characterizing soft and hard tissue, we can characterize treatment of the teeth. We can use right photon energy for treatment of teeth, gum tissues, and mouth structures, etc. We can go further, right, in photonics, towards neurophotonics applications, in order to activate, right, either activate or inhibit, right, signaling, inhibit signaling among neurons, right, nerve cells or neurons, etc. Treatment also we can use for treatment of neurons, or right, neuropsychiatric disease, etc. Can be taken care. And photobiomodulation is towards right, alleviate acute, chronic pain, etc. and wound healing. This are, of course, some of these approaches we will be learning in our classes, subsequent classes. Basically, they are all based on the photon energy and photon interaction with the tissues, etc. So, treating nerve cells, treating nerves, right, and injuries, structures, etc. Now, coming to the next aspect. So, when we talk about photons as such, how does photons or electromagnetic waves, right, light is nothing but an electromagnetic wave. So, photons or electromagnetic waves, when they right interact with the tissue, one aspect which is associated with this is what we should know is refractive index comes into picture. Refractive index comes into picture, right? When the light is getting transmitted through the material, the refractive index will right will affect the speed of light, right, transmitted through the tissue material, and that speed of light is, let's say, S is will be equal to C by N, where C is the speed of light in vacuum, or in free space. Approximately, we can say that it is approximately 3 into 10 raised to 8 meter per second, and N is the refractive index of the material. Okay, refractive index, it's a real part of the refractive index of the material, which right influences the speed of light transmitted through the material. So, some of those tissue right material, of course, air we consider refractive index as 1, and water, right, as we know, it is this 1.00, let's say 00, then water is 1.33, etc. If it is cornea, I am just giving you some typical right values based on the available literature. So, maybe here we can say 33376, right, small variation. If we are considering epidermis, it will be approximately 1.34 to 1.43. If we are considering cytoplasm, which is part of this cell, so it is right, it is between 1.35 and 1.350 and 375, etc. If we are considering human liver or right such organs, let's say liver or other organs, it is 1.376 to 1.380. Mitochondria, which is mitochondria, right, which is related to cellular level, it is 1.38 to 1.41. And tooth enamel, and the refractive index 1.62 to 1.73. Okay, and there is one more important characteristics associated with tooth enamel, is its birefringence characteristics as well. So depending upon the electromagnetic wave, right, or the polarization state, the refractive index experienced by the electromagnetic wave traveling through the medium will also depend upon its it will be varying depending upon its orientation, the speed. So it is basically birefringence characteristic of the tissue which, right, determines this speed in that case. And if we consider the whole blood sample, the refractive index is 1.355 to 1.398, etc. Okay, so these are all typical values, and they are useful for us subsequently when we are designing some of the devices. It helps us to determine some of the important requirements related to the photons, etc. Another factor associated with this material interaction is right, as absorption. Okay, so, refractive index is associated with right, dispersion and the speed, right, of the electromagnetic wave, while absorption is right, an important aspect related to when the photons or electromagnetic wave propagates through this medium, depending upon the medium characteristics. Okay, in terms of its molecular structure, etc., the absorption phenomena comes into picture, light absorption phenomena, and this absorption phenomena helps us basically to determine right, depending upon our requirements, what a photon frequency or wavelength, right, that we should make use of it for certain applications, maybe sensing, maybe therapeutic application, etc. Right. So if we consider x-axis as in terms of wavelength, let's say wavelength, right, in terms of micrometer is the unit, and y-axis, sorry, 1 minute, y-axis in terms of absorption coefficient. Okay, okay. And its unit is right, in terms of centimeter inverse. Okay, so when light right, propagates through the medium, for different medium, such as, let's say we consider maybe very simple one, water as such, then depending upon the wavelength it will be different. So here I'll just give you some idea about 0.1, 0.2, 0.5, 1, 2 micron, 5 micron, and 10 micron. Okay, micrometer, right? And here logarithmic scale in terms of absorption coefficient, 1, 10, 100, and 1000. The larger the absorption coefficient, the amount of light will get absorbed by the tissue will be much larger, right? So if we consider this, then what we will observe, I'm just trying to do a rough, right, this thing sketch in order to give you an idea. Okay, approximately this may be around 2.9 or so micrometer. Okay, this peak is around here, this peak is around 0.19 micrometer. This range, right, where we will see minimum absorption by water molecules is around, right, between in the near infrared, part of the visible range and near infrared range. If we consider protein absorption, which is quite significant in the near infrared range and slightly before, right, visible range. If we are considering let's say blood, right, a sample, then its absorption characteristics, right, goes in a different way. Okay, so this is a blood sample, this is water, right, molecule, this is a protein molecule. If we consider melamine structure, then it is this, sorry, not melamine, I'm so sorry, melanin, right, melanin, right, and this. So what this different such right absorption characteristics by different media indicates, it helps us to determine, depending upon our applications, what particular wavelength or photon energy should be useful, photon frequency should be useful for different applications. And say for example, if I would like, if we want to treat some of the tissue samples and remove right some of the tissues, etc., we would prefer high absorption band this electromagnetic spectrum, where the tissue material can absorb a large right amount of photon energy, so or indirectly photons, so that is around 0.19 micrometer. Or if we are working with right material where we would like to ablate, we can even use right 2.9 micrometer. It shows because absorption is quite large. When we are trying to measure or use it for sensing applications, depending upon the wavelength, right, absorption characteristics are different, and we make use of this different absorption characteristics to indirectly identify also or measure the concentrations of the presence of molecules by selecting appropriate wavelengths in the visible range or near infrared range. Mostly we measurements are in the range from visible to near infrared up to 1.5 1.6 micrometer or so. If we go towards longer wavelength, we end up with large amount of absorption. As we already know, most of this tissue structures, cellular structures, they contain 70% of water, so the absorption, typical water absorption, becomes predominant as we go towards longer wavelength, etc. So we would prefer for certain measurements applications in the range where such water absorption is low, at a lower side, so maybe near a visible range, near infrared range, etc. So this right aspects are helpful in terms of absorption characteristics. If we talk about photons, frequency and wavelength, so electromagnetic wave, EM wave, okay, its wavelength and frequency aspects, we know that electromagnetic wave being a sinusoidal right? Electromagnetic wave being sinusoidal in nature, the speed of its right propagation is nothing but right, a product of frequency and wavelength, and this is frequency is nu given by nu, this wavelength is lambda, speed of electromagnetic wave is right c over here. So, and electromagnetic wave spectrum, if we observe in terms of right its distribution, let's see in terms of so we can see that frequency of electromagnetic what we are interested in as for the biophotonics, right, application ranges from 190 nanometer to 10.6 micrometer, which is determined based on the absorption characteristics of the species, right. So beyond this range, absorption is so prevalent that right we may not be able to extract the exact information. And in terms of this is in terms of wavelength, right. In terms of frequency, speed of light we know, or electromagnetic wave, and if wavelength is known, frequency can be determined, which will range between 10 raised to 14 hertz and 10 raised to 15 hertz, right. Longer wavelength is shorter frequency, the small frequency spectrum, shorter wavelengths will end up with a larger frequency. In terms of photon energy, which is nothing but h into nu, where h is the Planck's constant, which is 6.63 into 10 raised to minus 34 joule second. Nu is the frequency of the electromagnetic wave, can help us to determine the photon energy, which ranges between 0.1 electron volt to right to up to maybe few electron volts, correct. And sometime, and this electron volt can be determined based on right this equation, simple E is equal to h nu or hc by lambda. H is constant and c is also constant in free space or vacuum, so we can that factor turns out to be 1.2406 with lambda and divided by lambda in micrometer, can give us right photon energy in terms of either joule or electron volt, corresponding electron volt also, okay. So this spectrum is useful in terms of understanding right that how photon energy can be determined based on the photon frequency or wavelength, right. And electromagnetic spectrum ranges from is right 190 which is useful spectrum, right, part of the spectrum for biophotonics application, ranges approximately from 190 nanometer to 10 micrometer or so, 10.6 micrometer. And in terms of various right standards, this spectrum is also expressed in terms of band, right, some of this frequency bands, right, frequency bands. So one is UVC band, they define the wavelength range is range in nanometer, okay, which is 10 raised to minus 9 meter, is 100 to 280 nanometer. So if it is B band, then 280 to 315 nanometer. If it is A band, then it is 315 to 400 nanometer. And visible range, so UV stands for ultraviolet, it has C, B and 3 band, is from 400 nanometer to approximately 700, right, nanometer. And if we consider near infrared range, near infrared IR infrared range, right, IR range, it is 750 or sorry 700 to 1500 or 1400 nanometer. Okay, and mid infrared range, right, is 1400 to 3000 or slightly longer, right, wavelength. And beyond this is far infrared, right. In some books, the mid infrared range may go up to 5 micrometer, and then beyond that is the far infrared, right. So 3002, right, 10,000 or longer, up to let's say 10,000 CO2 laser wavelength of 10.6 micrometer, right. So it is 10,600 nanometer also. So that will be the approximate, right, and corresponding energies can be estimated, right. It is nothing but h nu or hc by lambda. We know the wavelength, we can determine the approximate photon energy, and photon energy in the UV band etc. will be quite large, right. Few electron volts, few 10 electron volts, is 4 to 10 electron volts, and as the wavelength increases, so here we can say 12.4 to 4.43 electron volts, and as the wavelength increases, right, so finally we'll end up over here, mid infrared range, it is around 1.63 electron volt to 0.89 electron volts. Okay, mid infrared range. This is for UVC band, etc. So it can be estimated very easily. So this aspects are useful for us, as I told you, to determine, right, what interactions we are biological, optical means interactions we are looking towards. Now we will deal in the next class. We will try to see some aspects related to, right, biological cells and tissue, just basic introduction, so that when we talk subsequently towards discuss about biophotonics aspects, it will be very easy for us to understand. So biological cells and tissue, some basics, and then we will right, get into basics of electromagnetic wave or right wave or optical waves, in order to understand some of their physical, right, parameters in terms of polarization and their influence, wavelength, right, frequency, of course, phase, right, parameters related to phase of the electromagnetic wave, right. So these aspects which will be useful for us in terms of understanding some of these phenomena related to, right, scattering, reflection, absorption, transmission. Okay. So these aspects we will cover in the next class. Thank you very much.